the magic settings on this computer. See, I've used the same software in statics, and I have no problems with camera and mic yet. For some reason, over the past few lectures, it has not liked me very much. Okay, so I sort of went into grading overdrive yesterday on my other exams. I haven't uploaded the attendance grades yet. I'll have those uploaded probably by the end of the week. We're caught up, though, on homework grades. Like I said, my goal is to have the exam graded by Friday. Worst case scenario, it'll be the following Monday, but it's not going to be later than that because I want to get it to you and get moving on. I'm going to assign homework 5.1 today. That is due Friday. Homework 5.1 is going to be our first foray into the land of shear and moment. So essentially, other than when we start discussing software analysis and influence lines, we are done with trusses. We're done with them. Influence lines is a topic that we're going to discuss later. I was talking about it a little bit before I hit the recording, and it's about how to assess structures subjected to moving loads. And so we're going to sort of be looking at all structures within that context. So we're going to talk about trusses, but we're just going to sort of highlight them. But what we are going to be delving into head first over the next few lectures is beams and frames. That's what we're going to be talking about over the next little bit. So we're going to be talking about internal shears and internal moments, and specifically the relationship between shear and moment. Okay. Now, if you had me for statics and deformables, so you have seen shear and moment diagrams before, but we are really going to investigate them in here, and we're going to extend our discussion of shear and moment diagrams into some other ideas, so more advanced loading situations. We're going to also look at scenarios where graphical approaches don't really work, and so you kind of need to derive an equation to plot your shear and moment diagram. But deriving equations are also going to have important contexts later when we look at deflections. So again, we're going to take what we did in statics and deformables and really ramp it up a little bit. Just kind of like what we did with trusses, but I think with here it's a little bit more. Now, if you've ever been to I've said this before in other classes, but if you've ever been to like a Mexican restaurant or a Thai restaurant, and you look at the menu and there's the item that has the chili pepper on it, that means that item is spicy. Today's lecture should probably have something like that, because today's lecture has a little bit of calculus in it. I know, a little bit of calculus today. Don't worry, it's not bad, but we are going to be referencing some calculus when we look at the relationship between shears and moments, and ultimately we're going to use that to develop graphical means to plot shear and moment diagrams. But with that, let's go ahead and jump right into it. Let's talk about internal shears and moments. Now, the reason that we're talking about this is because we're wanting to cultivate a graphical approach to construct shear and moment diagrams. Now, I have here a beam, okay, and just to level with you, compared to what we did in statics, this is way more involved already. I mean, we were doing some pretty simple shear and moment diagrams in statics and deformables. This is way ramped up. But this is not going to be that difficult by the time we get done with them in here. But let's go back a little bit. So what are shear and moment diagrams? So I would argue that there are certain skills that civil engineering students just need to be able to do when they get out of an engineering program. Sieve analysis. You just got to be able to do that. Have y'all started doing that in 321? Yeah. Sieve analysis. That's just one of those things that you got to be able to do. Y'all talking about Bernoulli's equation yet? In fluids? Yeah. That's just like one of those things you got to be able to do, you know? When you get into soils and you start looking at soil phase diagrams like air, water, and solids, you just got to be able to handle that. Shear and moment diagrams is just one of those seminal skills you just got to be able to do as a civil engineering student. They are, in a nutshell, graphical representations of the internal response in a beam in terms of its internal shears and internal bending moments. And they are critical to design, okay? So, for example, with this beam, this isn't a plot of the internal shears and moments across the span. It tells me that when I'm designing this beam, I need to design for a worst-case positive bending moment of 460 foot kips, a worst-case negative bending moment of negative 100 foot kips. The positives and negatives can really matter dependent upon the type of material that you're looking at. For example, if I'm designing this as a reinforced concrete beam, concrete is a material that behaves very, very well in compression, but it hates tension, right? Concrete cracks under tension. The whole tenet of reinforced concrete design is you put rebar where the tension is, right? So this tells me I need a bunch of rebar in the bottom of the beam, but over here I need rebar in the top of the beam, okay? Because the top over here, the top is in tension. It's in negative bending. It's in frowny face. So I need rebar in the top. And those moments will tell me how much rebar to place. It will tell me how to size that element. In terms of shear, I need to design for a worst case shear of 46 tips. Honestly, in a lot of cases, the positive and negative shears don't really matter from a design standpoint. The magnitude, they do matter from an analysis standpoint, but not so much from a design standpoint. The magnitudes matter, however, because the magnitudes will help us determine the amount of shear reinforcement necessary in an element. So in concrete, we're talking about the spacing of stirrups that tie your rebar cage together. In steel design, we're talking about the behavior of the web. Maybe we can throw some transfer stiffeners in there and whatnot, but we aren't able to do that if we don't understand the internal response. These are, again, very seminal skills. And just about every single beam or flexural element that you design, you're either plotting a shear and moment diagram, or if it's a very simple case, you're using some plug and chug expressions to determine maximum shears and moments, but again, those are based on shear and moment diagrams. Now, again, what a shear and moment diagram is a plot of the internal shears and moments. So the first thing I want to do is I want to look at those internal shears and moments at particular points in the structure. Okay. Now, we've looked at this before. So if you samurai sword or lightsaber through an arbitrary point in a structure, you get 3 unknown internal components: an unknown axial force, an unknown shear, and an unknown moment. We have to choose a positive sign convention. So, for example, with axial loads, we sort of made a decision that we would consider tensile forces positive. There's no magic behind that when it comes to truss analysis. We could have assumed compression positive. We just didn't. We just picked one and went with it. With shears and moments, the sign convention that we choose is a little bit more critical because the graphical approaches that we are going to develop later are very dependent upon these internal shears and moments. Now, I'll level with you. In statics and deformables, we really didn't harp on these internal sign conventions all that much. We really didn't. In here, they're going to matter. Okay? So, if you cut a section and you look to the left, downward shears are positive. If you cut a section and look to the right, upward shears are positive. They're always going to be of equal magnitude and opposite direction. For bending moments, if you cut a section and you look to the left, counterclockwise moments are positive. If you cut a section, look to the right, clockwise moments are positive. That really matters, okay? That's really, really important in the analyses that we're going to do in here. So you got to sort of make sure that you're consistent on that, okay? And I'm going to be honest, it's one of those things that there's very little in the land of structural analysis that I believe really requires memorization. This is probably one of them. I think this is kind of one of those very, very few things that you ought to just have memory recall on. Get my notebook out. Okay. So I want to discuss just this concept today. I have a beam and I want to compute the internal shears and moments at a point. And I know this might seem very basic, and I'll level with you, it kind of is. But I want to start basic. And again, I think you find that I have sort of a theme in this class where we sort of start basic and we slowly ramp it up. And by the time it's all said and done, we're analyzing really crazy trusses and really crazy loading scenarios. It's the same story with this. So we've got a beam and we have a series of point loads on it. Hold on for a sec. Does this beam look familiar? It should, but we already done this. We computed these support reactions. I believe this was the very first example problem that we did. We took this beam, we analyzed it, we determined that AY was 35.8 kips, AB or BY was 32.2. We analyzed this beam previously in the semester. Okay, so we've already computed these reactions. One of the things I'll tell you is that in this module in the class, when it's appropriate, I will give you those reactions. Sometimes I will not, and probably with a lot of the shear moment diagrams, I won't. Because I think you actually need to engage in that computation, because when we get to our graphical approaches, you'll see that having an inherent understanding of why those reactions are what they are will become important to making sure that you've got a correct shear and moment diagram at the end. We're not drawing shear and moment diagrams for this example, which is why I went ahead and gave it to you. Now, what I'm going to have you do is I'm going to have you compute the internal shear and moment at a random point in the structure, particularly a point 12 feet to the right of support A. Okay, so I'm picking a point. I want to say, what are the internal shears and moments at that point? So here's the structure, and we are samurai sorting. We are samurai sorting and lightsabering right here. And this dimension is 12 feet, so we'll call this section 1-1. Get this out of the way. This is getting in my way. All right, so we're going to cut a section, and we're going to determine the internal shears and moments. Now, remember the method of sections when we discussed trusses. Remember one of the tenets that we said is that it does not matter in which direction you look, you will get the same answer. The same is true here. If I samurai sword or lightsaber through that beam right there and there is no internal response, that beam's falling down. It doesn't matter which direction I look. It just doesn't. But that doesn't mean that as the analyst, I have to make it hard on myself. If I was an analyst cutting a section, which way would you look? To the left or to the right? I'd look to the left. There's just less stuff over here. So I'm lazy. Let's cut a section and look to the left. Now, this topic does require a little bit of extra drawing. So we're going to say cutting a section and looking left. Let's see what we got. Okay. So we have our structure. All right. So let's see. We have our support condition here. We have a load acting upward right here. This is AY is 35.8 kips. And then we have another load right here. This one is 20 kips. And then here is our samurai sword cut right here. And this dimension is 6 feet. This is 6 feet. Now, next thing we have to do is we have to draw our positive internal responses, okay? So, shears. If I cut a section and look to the left, which way is positive? Down. So we're going to draw a downward shear. And moment, which way is positive?
Counterclockwise.
Counterclockwise. Okay? So I'm just going to call them V and M. We use the letter V for shears for two reasons. One, a lot of times when you're writing S's and 5s, they kind of get a little mixed up. And V for vertical, change in verticals. So that's why we use the letter shear, or V for shear. Okay, so summing forces. So the way that we're going to handle this is we're going to use the equations of equilibrium. I've got two unknowns. Now I can sum forces in the x direction, but that's not going to tell me anything because there's nothing horizontal. So I'm going to sum forces in the y direction. And this is definitely, so before we start writing this out, one of the things I want to say, when we started doing truss analysis, so there is one key difference I want you to sort of keep in the back of your head. When we did truss analysis, you know how, like, when in doubt, we would always assume tension, and if we got a negative answer, it meant it's compression. But with truss analysis, you could be a little bit more intuitive. You could look at it and go, well, the arrow is probably pointing this way and this way. You know, you could change the direction of the arrow based on what was going on. Don't do that with this, Okay. With this, you really need to keep consistent directions with your direction, or consistent directions with your unknown shears and moments, and just let the math work itself out. If it's positive, it's positive. If it's negative, it's negative. The reason why is because if you're consistent with your sign convention here, then the value that you get from an internal equilibrium check should match what you get on the shear diagram or the moment diagram at the same point. So the sign convention and sticking to it matters a lot more here than it did with truss analysis. So, what do we got? We got 35.8 kips up. Going down, we got 20 kips down. Then we have V going down. You could call it V. If you want, you could call it V. It's section 1-1, whatever you want to call it. I'm just going to call it V for this, but you kind of get the idea. 35.8 kips equals V plus 20 kips. So therefore, V is positive 15.8 kips. And to be clear, the direction doesn't really matter for these internal responses. Just like direction didn't really matter for truss analyses, more about whether or not it was tension or compression. Because if you have an arrow pointing to the right on one joint, it's going to point to the left on the other. So the right and the left doesn't really matter all that much. It just matters whether or not it is in tension or compression. Just like with shears and moments, it just matters whether it's positive or negative. Positive, negative shear, positive or negative moment. Okay, now with summing moments, what we're going to do is we're going to sum moments. And whenever you're conducting an internal check, the easiest place to sum moments is the section cut. Okay? Pretty much always, that's always the easiest place because you're summing moments where one of the unknowns goes right through it. You don't have to consider V as shear. That's a single one or a double one. Single one on third avenue. You don't see that very often. All right, so we're summing moments. So we've got 35.8 times a moment arm of 12 this way.
It's 36.8, isn't it?
No. It's 35.
I was looking over at your AY. It looked like it's 56.
Oh, so just, pointing out my handwriting was
okay.
to everybody. I see how it is.
I just wrote 36 to 35.
I'm going to fix it now. And don't hurt my feelings. So, 30. I'm just. All right. So 35.8 kips times 12 feet, and then we have 20 times 6 the other way. But then we have M. Remember that M is a concentrated moment. So we have 20 kips times 6 feet, but then we just have M. Remember when we were dealing with reactions, we didn't multiply the M by a moment arm, or the concentrated moment by a moment arm. It was just 20 foot kips or 60 foot kips. You just add, right? So we're sort of doing the same thing here. So we have 35.8 times 12, which I believe that's, what was that, 429.6. That's foot kips equals M plus 120. So therefore, M is, in this case, also positive, and it is, was that 309.6? And that's it. That's your answer. That's really the skill that I'm trying to cultivate today. That's it. And I want to be crystal clear that if we were to cut a section and look to the right, so what would happen if we cut a section and look to the right? Well, we would just be considering everything on the other end of the section, but we would have a V arrow going up and a moment arrow going clockwise, right? Other than that, same process, I guarantee you'll get a positive 15.8 kips, positive 309.6 foot kips. We could take a look at that if you'd like. let's see if we can do some mental math, at least on the shear. Okay? So if we look at the shear, what do we have? So if we look here at the shear, what do we have? We have 30 going down, 18 going down, so we have 48 going down, right? We have 32.2 going up, so how much has to go up? 15.8. And upward shears this way are positive, so the shear is positive 15.8. Does that make sense? So I guarantee if we do the moments, we're going to get the same thing, because it's going to be 32.2 times this, 18 times that, 30 times that, and we'll end up having a net difference of 309.6. It doesn't matter which way you look, you're going to get the same answer. If anything, looking both ways is a check that you're getting the same thing. Does that make sense? All right, any questions on this? Okay. Now let's talk a little bit about some other tidbits that are going to pop up. Okay. I want y'all to pay attention to this. This is important. I have been teaching this class for a long time, and I have seen what happens during homeworks and celebrations of learning. I have seen the mistakes that pop up, and I want to avoid them. I want you all to get hundreds. Makes grading them a lot easier. Go ahead, that's the only thing I care about, right? I don't care if you'll learn it. I just want my job to be easy. I'm kidding. I'm kidding. All right. Let's go back to idealizing distributed loads. I want to talk what happens when you cut sections through distributed loads. Okay? This is a common mistake that happens. I want y'all to pay attention to this. So, when you're computing reactions, what do we do with distributed loads? We idealize them as concentrated loads, right? So we take a distributed load, let's say 2 kips per foot over 30 feet, and we idealize it as a 60 kip load right smack dab in the middle, right? Same thing with the triangular load. We take the triangular load, the magnitude of that load is equal to the area of that triangle, and then we put it a third of the way from the big end. Sound good? So watch this. Let's say I have a beam. Let's take a look at this beam. So I got a beam. It's got a 35 kip reaction on the left, a 65 kip reaction on the right. I got a 40 kip load over there on the right end, but on the left end, I got 2 kips per foot over a distance of 10 feet. So when I computed those support reactions, I said, okay, let's idealize that as a single concentrated load of 20 kips. Let's put that 20 kip load 5 foot from the A support, right? That's normal. We've been doing that this whole semester, right? But now, let's say that I say, hold on, let's samurai sword or lightsaber through that sucker. All right, let's samurai sword or lightsaber, and let's determine the internal shears and moments right here, okay? So I cut a section. Let's say that I look to the left. So I look to the left, all right? So here's the section, there's the distributed load, there's the 35 kip reaction, shear, moment, right? Distributed load. I take that distributed load, turn it into 20 kips, right? No, that is a different load than this. This load was 10 foot long. This load is 6.5 foot long. So now this load is not 20 kips, it's now 13 kips. Because it's 2 kips per foot over a distance of 6.5 feet. So it's a new concentrated load, new location. Okay? I can't tell you how many times I've seen students put 20 kips down here. No, don't do that. Okay? That is not good. All right? I've seen that happen all the time. Okay? You need the distributed load needs to be reassessed. That concentrated effect needs to be recomputed. Okay? When we do this, we are idealizing this as a concentrated load simply for making the computational support reactions easier. Like we turned this into a 20 kip concentrated load just to make figuring this thing, these two, easy on us. But that's not what's really going on the beam. Okay? If I had 200 pounds to put on this table, what's worse, spreading it out over the length or lumping it right in the middle? Lumping it right in the middle. And so if you just carry this down, you're not correctly representing the internal response inside the beam. Okay? So this is very, very important. I want to make sure that you all see this. Okay? Does anybody have any questions on this? Everybody good on that? Somebody in here is still going to do this. I don't want that to be the case. So make sure that you've got this in the back of your head. Okay. Now, what we just did, and I'm going to give you a homework problem just on this. It's going to be really easy, all right? But what we just did was determine the internal shears and moments at a single point. Like cut a section, get the internal shears and moments right here, just at this random point. But no, I want, and that's great for spot checking, but I want the internal shears and moments everywhere, along the entire beam, like what I had in the initial slide. What that basically means is if I have an internal, or if I have a beam and I get the internal shear moment here, and the internal shear moment here, here, or get it everywhere, basically we all know that if you have a bunch of points along a given axis, that an easy way of visualizing that is to plot it, or to graph the shear and moment along the beam, okay? That's what a shear and moment diagram is. So we just determined the internal shears and moments at a point. All a shear and moment diagram is a graph of those shears and moments if we cut the section everywhere. That's it. But you and I know we're not going to do that. We're not going to cut 100,000 sections and you know, record it and plot it in Excel. We want a simpler way of doing this. We want to be able to figure out a way of graphically figuring out what the shears and moments are everywhere. Okay? Maybe we can be a little bit more intuitive on this. So, I got a beam. Okay? Here's a beam. We'll call it simply supported. We'll keep this simple. All right? And I've added a couple things to it. So the first thing, I've got a coordinate system. So, just an x-axis and a y-axis. And I've got this load on here. And I'm just calling it some variable load W. Okay? It doesn't matter what the magnitude is. It just keep the idea that it kind of changes. And I have applied that load upwards. And that just makes the math a little bit easier because I'm doing it along the positive y direction. So that's why it's going upwards. So, all right. Now, in order to investigate the relationship between shears and moments, what I'm going to do is I'm going to slice out a small little element and zoom into that element. And we're going to call this element dxy. Y'all remember that term dx from calculus? What's the deal with dx? Yes, but it's a really tiny, differentially wide element. It's really small. Keep that in the back of your head. Really, really small. So let's take this element and let's zoom into it. So this is zooming into that element, and let's look at what's going on. Now, the load is variable along the beam, but we're talking about a very, very, very thin little element of the beam. And along that small, teeny, tiny width, I propose that we can treat that load as constant. It's a differentially small element, so we can just treat that as constant. Okay. Now, what I've got here on this element is I've got my shear. So let's take a look at the shears. So this is a section cut on the right, so positive shear up. This is a section cut on the left, positive shear downward. But notice what I've got. I've got the shear, and then I've got the shear plus some change. And so what this is saying is that from here to here, the shear changes. I don't know how much yet, but I know that it changes a little bit. Or I'm assuming it changes a little bit. We're going to figure out how much that change is. Same thing with the moment. Positive moment, but I've got some moment over here and some moment plus some change. And we're going to try and figure out what that change is. Because the idea is if I can figure out how much the shears and moments change from one point to another, well then I'm in the lane where I can start plotting some stuff out. So, let's make sure some notes. So again, we can assume that the load is constant over that element since it's so tiny. And again, we've added the dV and the dm element to indicate that it changes from one point to another. I should have just hit the button and read that, but no, it just came from my memory. Okay, equilibrium. So let's look at equilibrium. So we've got this differentially small element of the beam, okay, and we're going to apply equations of equilibrium. Okay, so let's start off with some of the forces in the y direction. So what do we got? Okay, we got V going up, we got V plus dV going down. And what about this? It's not W going up, it's W over the length of that element. So W dx going up, right? Does that make sense? Okay. So, V plus this equals V plus this. The V's cancel. And I get that change in shear is equal to the magnitude of that load. That's an interesting way of saying that. The change in shear is equal to the magnitude of the load. That's important. Change in shear is equal to the magnitude of the load. Okay. Now, before I go to the sum of the moments, remind me. Okay, so dx is really, really small. What happens if you take a really small number and you square it?
It's really small.
You get a really small number, right? So let me show you what's going to happen on the sum of moments side. So when I sum moments, I just pick the side. It doesn't matter if you pick the left or the right or wherever, it doesn't matter. I just sum moments here on the right. So if I sum moments here on the right, I don't have to worry about this shear. So what do I got? Okay. So on this side, all I've got is this moment, m plus dm. But what do I have on the left? Okay. So I've got m, got that. I've got v plus or v times dx. So v times dx over here. But then look what I did here. Look at this. So I've got the load, which is w dx, times the moment arm. What is the moment arm? Well, I idealize that as a single point load halfway over. So that's how I get this. Does that make sense? So the load is w dx and the moment arm is half of dx. Does that make sense? Now I know why my equilibrium's off. They took the screen down. It's not here. I was like, something's weird with how I'm walking around today. Now I know why. They didn't take this one down, but they took that one down. It didn't hit me until just now. Okay. So when I chug this out, I get m plus v dx plus this. Okay, and notice how I'm canceling out. I'm canceling it out because it has a dx squared term in it. So dx is a really small number, and then when I square it, I get a really small number. So we can neglect what I'm calling those higher order terms, and I get this. The change in moment equals the magnitude of the shear. And if I look at these relationships, I can take these equations and rewrite them a little bit, and by golly gosh, like I said, we're going to be in the land of calculus a little bit. Now, I want to be clear, we're not going to be directly computing a lot of derivatives and integrals when we plot shear moment diagrams. So I just want to level with you. We are not going to be doing that. But what I will tell you is that understanding this relationship is going to be a great spot check. So as an example, we're going to have a problem a little later in a couple lectures from now where we break out some Microsoft Excel to plot a shear and moment diagram. And we're going to plot the shear and moment diagram for a beam subjected to a triangular load. And what we're going to find is that our graphical technique doesn't really work all that well, because when you look at what the shear diagram and the moment diagram look like, you go, oh, dang, how do I deal with that? And so deriving an equation actually works out a little better. And so if you independently derive the shear equation and the moment equation, you can actually take a look at them and go, well, is the derivative of the moment equation equal to the shear equation? And if the answer is yes, then that's a check that you did it right. So we're not actually having to do the derivatives, but we are being able to check that is actually a little bit of a handy tool in your toolkit. Now, what is valuable about this is understanding the relationships between derivatives and integral patterns when you plot things. Let me ask you a question. What is the derivative of x squared? What is the derivative of 4x squared? Okay, so now let me ask the question a little bit differently. If I were to, okay, so if I were to plot x squared, or plot 4x squared, or 6x squared, or if I were to plot 3x squared plus 2x plus 8, what do I call those graphs? What are the names of those graphs? Parabolas, right? So if I graph anything where the highest x term is x squared, that's a parabola, right? Now, if I take the derivative of that term, and I get like 2x plus 3, 6x plus whatever, what's the graph of that look like? A line. So are you telling me that the derivative of a parabola is a line? So is the integral of a line a parabola?
Yes.
Yes, right? Does that make sense? So what is important is this, okay? I'm not saying you are going to be doing a lot of differentiation and integration, but what is important is being able to handle these relationships, right? Because I started saying things about how the change in shear is equal to the magnitude of the load, right? So really what that means, and we're going to talk about this in more detail over the next few lectures, but if you want to plot the shear diagram, you are integrating the loads. And if you want to plot the moment diagram, you are integrating the shear diagram. That's what you're doing, right? I mean, that's what our relationship tells us, right? I mean, our relationship says that the shears equal the integral of the loads because we just rearrange this. The moments equal the integrals of the shears because we just rearrange this. Now again, I'm not saying we're going to do a lot of calculus, but the patterns matter. So for example, if we have a uniformly distributed load, 2 kips per foot, a constant load, I propose the shear diagram is going to be linear. And I propose the moment diagram is going to be quadratic. Okay? Does that make sense? Those graphical relationships are really going to be important. Another thing that's going to be important is making sure that you can recognize slopes. What's the deal with that slope? Is it positive or negative? Positive, right? Positive slopes go like this. Negative slopes go like this, right? Make sure that you can recognize that. That's important, okay? That stuff's really important because it's going to matter when we start plotting shear and moment diagrams that you recognize what should be positive and what should be negative. Trying to think if there's anything else worth mentioning right now. Probably not, because we're going to delve into these a little bit. This is what's important over the next few lectures. Sound good? I'm going to let you out a little bit early. That's all I got. I'm going to pull up the QR code, but I'm going to see you all